conferencista, váyanse sentando en sus lugares correspondientes. We welcome our next speaker, Dr. Ryan Zeigler, who will tell us about Apollo and Artemis samples, what we know and what we will know. Dr. Ryan Zeigler is the Apollo sample curator and the Artemis curation lead at NASA Johnson Space Center. In his role as the curator and as the Apollo sample curator, he works with scientists around the world to provide them the samples they need to successfully achieve their research goals. As the Artemis curation lead, he is helping the Artemis mission prepare to bring back the next samples from the moon in a way that maximizes their impact on science. In his own research, Dr. Zeigler works with lunar samples to better understand the types of materials found in the lunar crust, and better understand how the moon formed, how it evolved, and how billions of years of impacts have altered it. Next, we give the floor to Dr. Zeigler. Please, Dr. Zeigler.
Well, good morning, everybody. Let me first say I'm really excited to be here. I'm really happy that Charlie asked me to come back. We did this about 4 years ago, and that was a blast that time, and I'm having a lot of fun this time so far. So I will also apologize that I'm giving this talk in English because I tried to do this in Spanish. I spent about 30 or 40 minutes and managed to translate one slide, and figured no one would understand it anyway, and so I thought, I will just do this in English, and I will try very hard. I get excited, and I tend to talk fast, and I will try to not do that. And so if I talk too fast, just wave it. So, right. So I'd like to actually talk to you about sort of three different but related things today. So the first thing I'm going to talk to you about is the Apollo samples and how we curate them, how we take care of them at NASA, and what we've used them for the last 50 years. We've learned a lot from the Apollo samples. And then very recently, the second part will be about some new Apollo samples that we'd never opened before, but we opened them very recently. And it was a very special project called ANGSA. It stands for Apollo Next Generation Sample Analysis. You don't have to remember what it stands for, just ANGSA. And so that was a new study of samples. And then at the end, we'll talk a little bit about Artemis. Now, we don't have Artemis samples back yet, unfortunately, but they're coming soon, and we're doing a lot to get ready for it. Right, so I work in the Astromaterials Acquisition and Curation Office, and so I want to show you where I work. Here's NASA Johnson Space Center. Oh, sorry, the space shuttle's in the way, but they actually couldn't have planned this better because they pointed the space shuttle right at our buildings. And so these three buildings house all of the different astromaterial collections that we have at NASA. And so we're only going to talk about Apollo today because even in an hour, we don't have time for all of that. But we'll talk a little bit about what we do in general. So there's a lot of words on here, but what this is telling you is what we do in astromaterials curation. So our main job is to keep the sample safe. So if it's a rock from outer space that belongs to NASA, it's our job to take care of it. Our job is not just to hold onto it and never let anyone touch it. However, we want to get as much science out of the samples as possible. So we're always trying to find the balance between handing samples out to scientists so that they can study the samples, but preserving enough for the future so that future generations of scientists can study them as well. And so probably 2/3 of what we do is take care of what we have. And the last third is getting ready for what's coming back next. And so we call that advanced curation, and it's how we get ready for the next mission. And right now, the next mission is the OSIRIS-REx mission. And we've spent the last 12 years getting ready for the OSIRIS-REx samples that are going to come back in 2 weeks, and I can't do math, on September 24th, however many days that is from now, 2.5 weeks. So if we were going to reduce what we did onto one slide, here you can see sort of a graphical representation of all of the different collections we have. And starting on the left, that was our first collection, the moon rocks, and the best collection, which I'm required to say, or Andrea will tackle me off the stage and the talk will be over. So we got those back in 1969, and then over the last almost 5.5 decades now, we've added more collections over time. And so we have a lot of different types of samples. So the Apollo samples and the meteorites, they're big rocks, and you'll see those after the break. We're going to have them out on the table. But then more recently, we've brought samples back from comets, from asteroids. We've partnered with JAXA. I mean, partnered is a strong word. JAXA has had successful missions that they brought samples back from asteroids, and they have been shared those with NASA. And then, so this is what we have now. And then this is what we're getting ready for. And so the next thing I said before was OSIRIS-REx. So literally 2.5 weeks. So I've worked at NASA for 12 years. And that was about when the OSIRIS-REx mission was selected. So for the last 12 years, my entire time at NASA, it's been OSIRIS-REx, samples coming from an asteroid sometime in the distant future. And now the distant future is only 2.5 weeks away, and we're all freaking out. So glad this wasn't next week, or I wouldn't have been able to come. And then it's not just that. Well, eventually we have Artemis samples coming back. JAXA is the Japanese Space Agency is going to have another sample return mission from the Martian moon, and then obviously Mars samples and eventually comet samples that we collect on the surface of the comet. So a lot to do, but we're not going to talk about all that today. So I don't have time to go through all the labs in lots of detail, but I will talk at a high level about the 3 basic parts of what we do to keep the samples safe. So we have to keep the samples safe, and for us, that means to keep them physically safe, but also to keep them clean. If we accidentally contaminate the samples with water or any compound that they didn't have in their natural environment, it will invalidate a study that some future scientists might want to do. So we store all of the samples in clean rooms. And now each clean room, each type of sample, each of the 8 types of sample have a different type of clean room, and they are tailored specifically to that type of sample. And we'll talk more in detail about the Apollo clean rooms a little bit later. But here's just some pictures of the different types of, that's stardust in the top right, and then these are cosmic dust particles, and then this is the Genesis lab, and this is the meteorite lab. And so, they're similar, and we wear suits to keep the room and the samples clean, but we'll see the Apollo samples a little bit later. So keeping them safe isn't just, this is like the front of the house, if you've ever worked in entertainment. And this is the back of the house. So this is actually the most important part. Keeping the lab clean wouldn't be possible without this. When I got my PhD in geology, I never thought I would be super excited about air handlers and ultra-pure water systems and liquid nitrogen systems. But we have a multi-million-dollar plant that provides us with clean water, clean air, and clean gas, and that's what we use to keep the samples safe. And a huge proportion of our time goes into keeping these running in the Houston area. So, we have this giant tank of liquid nitrogen, which is, oops, that's not the right button. There, that's 17,000 gallon tank. Oh boy, 55,000 liters of liquid nitrogen that we have to refill every week, and that's what gives us the gas for all of our labs. And so. These always break, and then we fix them, and then they keep it up and running. And then the last part is actually the physical security. So we actually have to keep people from getting at our samples who aren't supposed to. And so we have lots of physical security at Johnson Space Center. There's security perimeter. The building itself, the building 31 North here, is a hurricane-resistant building. I used to say it was a hurricane-proof building, and I got yelled at that I was tempting fate. So we are good for a Category 4 hurricane, and then we store the Apollo samples in particular in a huge vault so that the samples are physically secure. And then just in case all of this fails, 15% of our samples are actually not stored at Johnson Space Center. They're stored at our secret remote storage facility in White Sands. So not really a secret, but I like to say that. So I won't tell you where at White Sands though. So. And that's the picture you can see here in the bottom with Melissa. That's her bringing out the Genesis samples out to Genesis. And I promised Melissa I would stop using that picture, so no one tell Melissa. All right, so that was sort of the general overview of what we do. But now let's, I've highlighted moon because, like I said, lunar is better, and we'll talk about that for the rest of the time, I think. So this is my favorite picture of the moon. It is not the best picture of the moon, but it is my favorite picture of the moon. I'd seen this picture many times, and it wasn't until I realized the date on the picture July 21st, 1969, that this picture was actually taken by the Apollo 11 astronauts on their way back. And if you're looking at it thinking, well, the moon looks weird, it is weird, because it's all on its side. That's the South Pole, that's the North Pole, so everything's been flipped. They didn't know what they were doing. But it's a great picture. And the reason I show it is because if we're going to talk about Apollo and what sets Apollo samples, the moon samples we have, apart from other collections, it's how they were collected. So the Apollo missions utilized the Saturn V rocket, which is still, I think, the largest, most powerful rocket ever to be used on Earth. And so we'll talk more about that at the end when we talk about Artemis and their new rocket and whether it's bigger or not. And hopefully there's no one here who knows better than me. But a lot of people, I mean, Apollo was as much political as it was scientific. During the 1960s, it was about beating the Russians and then the Soviets. It was about the U.S. beating them to the moon. And a lot of people want to know, like, why did the U.S. win and why did Russia not win? And mostly it comes down to this rocket. So our big rocket was better than their big rocket. Their big rocket kept blowing up. And if your rocket blows up, it's hard to get anywhere. And so the Saturn V was just this amazing achievement, and it was at the core of everything successful that came out of the Apollo mission. And because it was so successful and because it was so big and powerful, it was able to deliver astronauts to the surface of the moon. And this is the other way that the Apollo collection is different than all of our other collections. They were collected by people. And so astronauts are really good geologists. They're not as good as geologists. They're really good geologists even though they're fighter pilots, at least during the Apollo era. And so because they had such a big rocket, they were able to deliver the astronauts to the surface. So there were 6 different missions that landed on the surface. Each had 3 astronauts on it. Each one had 2 astronauts who went to the surface. And they were able to bring in a wide variety of different tools and even rovers. I think that's a coffee cup, I'm not sure. But they were able to, the astronauts with these tools were able to do more in just a few days on the surface than, say, the Mars rovers have been able to do in 8 to 10 years on the surface. And that's not making fun of the Mars rover, because it's done amazing things, but it's the limitation of robotics versus people when they're involved with space exploration. People are much more capable, because you can make a robot do what people can do, but it costs a fortune. And so, right, so that's the people part, but more importantly, how about the samples, because that's what I get excited about. And so here is the near side of the moon, and the red dots are the 6 places that we landed on the surface of the moon. And we're not going to step through each one individually, because everyone will fall asleep, but what we will look at is this one up here. This is the Apollo 17 site. And here's a nice picture of the surface of the moon. It's the Shorty crater at the Apollo 17 site. And you can see one astronaut has wandered off and took this beautiful panorama of the area. And what I want to highlight here is the diversity of samples that came back. And so there's a whole bunch of different sample types that they were able to collect. So you have basalts, let me make sure I'm doing them in the right order. Basalts and anorthosites, these are igneous rocks. These are rocks formed from molten rock, like what comes out of the volcano over here, the basalts. And so they were able to collect these, but then they were able to collect the anorthosites that came from the highlands. And then more importantly, they were able to get breccias. And not more importantly, but because the moon has no atmosphere, it is getting hit by thousands of tiny impacts every day, and the entire surface has been churned into dust, into regolith. And they collected that as well, so that fine-grained dust that's everywhere. And so they brought back the regolith, they brought back a wide variety of rocks, and they even were able to bring back what we call drive tubes and drill cores. And so they were able to use a deep drill and drill down 3 meters into the surface of the moon, and they were able to use what are called drive tubes, where they were able to hammer into the surface. And if you're wondering why I'm talking about this, it's because the whole second part of the talk is about one of these drive tubes. So pay attention, there will be a test at the end. Right, and so just to summarize, there were 6 sample sites. We had almost 380 kilograms of sample, almost 2,200 individually numbered samples. And like I said, there's a wide variety of samples that came back. Where they came back from was relatively restricted on the moon. It's a small area of the near side, and that'll be important. That's why we're not going to that area for Artemis, one of the reasons. And we had really good geologic context because we had the astronauts on the surface, and they were able to take a lot of pictures. So just having a rock and not knowing where it came from really limits what you can learn from that rock. If you have that rock and a bunch of pictures of where you collected it or other information about where you collected it, it makes the rock much more powerful. So here is in detail one of our curation labs. This is the lab where Charlie used to work. This is the lab where Andrea, my colleague, still works. I point the laser pointer at Charlie, but I might I don't know if his sunglasses are rated for laser pointers. Right. So we store the samples in a vault. That's the top picture. Inside these stainless steel cabinets that are filled with a very special gas called, with a special gas mixture made out of entirely nitrogen. Nitrogen's not special, makes up 80% of our atmosphere. But because we don't want the rocks, the moon rocks, to actually rust, we don't want them to weather, we keep all of the oxygen and water away from them. So we store them and we work on them inside these cabinets. And we're very picky about what we let go into the cabinets. The only things that are allowed to go into the cabinets are made out of stainless steel, they're made out of aluminum metal, and they're made out of Teflon, and that's pretty much it. Now those will contaminate the sample, but we know what those contaminants are, and they're easy to spot. They don't occur in nature, and so we can back that up. Right, so why are we still studying moon rocks? So I started grad school, and this is embarrassing to say, 25 years ago. And my first day of grad school, I met my new advisor, and I sat down across the desk from him, and being a bad student, which I was, I didn't do any homework, and I had no idea what the guy did. I'm like, what do you do? And he's like, well, I study moon rocks. I'm like, really? It's 1998. We had those 25 years. You guys haven't figured all this out? It was almost my last day of grad school. So just don't do that. Don't insult your advisor on the first day. But he told me at the time, and it's funny that 25 years later, here I am talking to people giving the same answer, is that new scientists come up with new ideas. And new instruments, as the decades go on, become more sensitive, and we can do more with less. And so, yes, we don't have any new samples. There aren't magic new samples that we don't know about from Apollo, but we are able to study those same samples in more detail and learn more things. And so that's why we're still studying them. And that's reflected in this. You can't give a talk without showing at least one graph. So I made this graph, which just shows all of the different samples and sample requests we get. So, going on almost 53 years now, we've had over 3,385 different requests for samples. We get, on average, about 60 requests per year, and we're still getting 60 requests per year now. Now, it hasn't been every year. You look at I put it on a log scale to hide, there was a few bad years in the 1980s and 1990s that we didn't get a lot of requests, but we're still handing out 700 individual pieces of the moon every year on average to scientists. There are 145 different scientists in 18 different countries around the world who are currently studying the Apollo samples. And we expect that number to go up when we get to Artemis. So what have we done for the last 50 years? I know this is a wall of text and there are no images, and I apologize for that. It's a NASA talk. This is how we're supposed to do it. Trying to summarize everything we've learned about the moon in the last 50 years into one slide or even a few slides was very challenging. And I don't want you to try to learn everything we did. But what I want to point out is that Apollo samples have been very useful, not just for studying the moon, but for studying other planets as well. So we learned really big, important things about the Earth and the moon. We learned how old it was. We learned that the moon formed through a giant impact into the Earth. We figured out that the moon had an ocean of magma that covered the whole thing. And that's fairly obvious. You're studying rocks from the moon, you should learn something about the moon. What's less obvious is that we've also learned about every other solid body in our solar system, like the ages of, if you look at a map of Mars, you'll see things like the Amazonian terrain is X billion years old, and the number that goes in front of the X, the age of the Amazonian or Hesperian terrain on Mars is based on studies of lunar samples. We don't think necessarily that Jupiter, Saturn, Uranus, and Neptune formed where they are currently found. We think maybe they formed in much closer to the sun, and that there's a whole new model for solar system dynamics called the NEAS model, which I think is now there's another one called the Grand Tech model, but there's all these models. But one of the main things the models have to do is account for the ages of moon rocks, and it actually is really helping us learn about the gas giants, which you wouldn't think. I can't work Pluto into the discussion yet, but our solar system rotates around the center of the galaxy, just like the Earth rotates around the sun. And where our solar system is in the galaxy, the radiation environment changes. There are different things that change, and there's a record of that in the moon rocks. So the moon rocks even let us study our entire solar system and its place within the Milky Way galaxy. And right now, the moon rocks are the only thing that let us do most of these. All right, so that's part one. So just to summarize, we take really good care of the rocks. We've learned a lot from the rocks, and we're still studying them. Okay, so an hour is a long time to listen to me. So we're just going to take a breath for a second. I'm going to show it's not really an embarrassing picture of Charlie. I couldn't find that, but show you a picture of Charlie back when he still worked at NASA, and Andrea. One of them looks exactly the same, and one of them looks different 10 years later. I'll let you decide who looks different, but here you can see another picture in the lab. So, right. Okay, so part 2. Now I want to talk to you about ANCSA in detail. So I said there were no new Apollo samples, and that was a little bit of a lie, because I work for the government, and it's our job to lie to people. And so there are 6 Apollo samples that were never opened. So there were 2,196. There were 6 that were never opened. They were intentionally saved so that they could be studied later. And the reason for that was mostly because they realized that the instruments at the time were not sensitive enough to make the measurements they needed to. And if they tried to make them in 1975, they would lose the opportunity. And so we saved a few of the samples to the future, and the future just never came. And then in 2019, when there was the 50th anniversary of Apollo and people were really interested in the moon, and the fact that Artemis was coming, we were able to get enough money to bring together some groups of scientists to study these in detail. And so NASA selected 9 different teams of scientists to study the 3 samples I'm going to show you in a second. It was like 80 people total. Now, our job on the curation side was to open and characterize and hand out the samples to the scientists. And part of what we were doing, we had done before, but not for a long time. And a lot of what we had to do for this project was completely new. And we're going to run out of time if I try to talk about everything. So what I'm going to try to do is highlight a few of the things that we had to relearn how to do, and for a few of the things that we had to apply to Apollo samples for the first time. And one of the big drivers of this was Artemis. We knew new samples were coming back from Artemis, and we could just do everything exactly like we did Apollo in 1969 or 1971, but a lot has changed in 50 years, and so there are better ways to do it. And so this whole project was a way to get ready for samples for the future. So, what samples did we select? I said there were 6. I'm not going to show you all 6. I'm just going to skip to the end and show you the 3 we selected. So we selected 3 samples. The first 2 are what we call drive tubes, and they're actually what we call a double drive tube. Now, they are 2 different hollow aluminum tubes that you screw together. Each tube is 35 centimeters long and 4 centimeters in diameter. So total, well, I don't know, math's hard again, but 70 centimeters. And the picture on the top shows how we use them. Oops, that would not be the right button. So the astronauts literally hammered the hollow tube into the surface, and then they pulled the tube out. Then they unscrewed it into 2 pieces, put caps on the end, and brought it back. So it's a really simple thing, but it's really powerful. What's better about this than just taking a scoop of regolith is the stratigraphy. The layering within the sample is preserved. So with a scoop of regolith, you can study the regolith as a whole, but you don't know whether you're studying the surface or the middle or deeper within it. Within these drive tubes and within the deep drill cores, we're able to study the surface and 5 centimeters down and 10 centimeters down and whatever depth you like up to however deep it goes. And so what made this one special was that there were 2 drive tubes. One came back normal, meaning they capped it on the end and they brought it back and it actually saw a little bit of atmosphere before it got into our cabinets. And so it was what we call unsealed. So it had some information in it, but the bottom part of that, 73001, was very special because they put it in a second tube. So they took the aluminum tube that you can see here, and they put it inside of the stainless steel tube. And the stainless steel tube had a very special top on it where it had 2 types of metal, one soft and one hard. And you screwed very hard, and you drove the soft, hard metal into the soft metal, and it made a vacuum seal. And so we think it preserved lunar vacuum all the way back to Earth, and then once they got it here, and they weren't ready to open it, they thought, this isn't going to last 50 years. So they put it in a secondary container, and we'll see that later. So we have 2 samples, 73001 and 73002, that go together, but one was sealed under vacuum, and we think has gas from the moon in it, which has never really been studied. And so this was the main part of what we were going to do. The other thing we had was 1 frozen sample. So we had this basalt you can see up there, and if you're thinking that doesn't look like it's in a freezer, it's because it's not. So it was collected on the surface of the moon. It was brought back under normal conditions, say 25 degrees Celsius plus or minus 5. But once we got it back, they decided to freeze that 1 sample away in a nitrogen atmosphere, and they just left it sitting there for 50 years as a way to study it in the future to see if storing samples at 25 degrees Celsius in nitrogen is a bad way to do it. Be a little bit too late. We've already ruined the other 2,190. It's a good way to do it. It turns out it's great. But we had never processed samples in the cold before, and so figuring out how to do that was a challenge. So we'll spend a little bit of time going through. So just to put these in a little more context, we're looking at the Apollo 17 site, and the white lines are where the astronauts walked, and the numbers are where they picked up samples. And that double drive tube I talked about, I covered up the 3, is right there. This was an exciting sample because it came from this landslide deposit, which is outlined in blue. It's sitting on top of a fault, and we're hoping that sample, or we were hoping, and it did, that sample had information both about the landslide and about the fault. So it was a special sample among the special samples. And then the frozen sample came from right over here from Station 1, and all of it came from Apollo 17. And so that they were able to use all of these different types of samples to learn more about the Apollo 17 site. So, getting the gas out, that was sort of step 1. If you're thinking I skipped 73002, I did. We're not going to talk about 7. We're going to talk all of our time talking about 73001. So 73001, last spring, we decided it was time to get the gas out. So the engineers in 1972 didn't do us a favor. They built this special, this tube that would hold the vacuum on the moon. They didn't build a way to get the gas out of it. There's no valve on it, there's no other thing. They're just like, somebody smart in the future will figure it out. Unfortunately, we didn't have someone smart in the future, we had me. So I am not I'm not somebody who studies gas, so I went and I found smart people who study gas, and they helped us. And so what we decided to do was to extract the gas using differential pressure. And so we partnered with a group at Washington University in St. Louis who do this for a living. We basically paid them, and they built us this gas extraction manifold. This is the inner vacuum container, and I said that once it got back to Earth, they put it in a secondary vacuum container that they were sure would hold vacuum for 50 years, and it did, and that's that. So we had to figure out how to get the gas out. So this long tube right here hooks up to the valve on the end of this, and so like this. And you can see them doing all the work. That's my deputy, Juliana, and these are the folks from WashU, and they're doing a good job. Not everything went super smoothly, as usual. You can see that Juliana has had enough of the ultra-high vacuum. Well, I won't use the language she uses, but there was a lot of swearing, some of it in German, some of it in English. But in the end, it was relatively straightforward. We hooked up the vacuum container to this tube. We pumped the vacuum down in here to 10 to the minus 9 torr, so super low vacuum. The pressure in this tube was higher. We opened the valve, and because that's how gas works, the gas equilibrated between the container that it was in and these empty canisters that we had preserved. So we were able to capture the gas from the outer vacuum container in these outer containers, and then we have been providing them to scientists to study. If you're thinking, that's not that bad, you're right, it's not. What came next was the part that was hard, and the part where we didn't get any favors. So now we had to open the outer vacuum container and take the inner vacuum container out of it. We did that inside of our cabinet, and you can see the process of doing that here. We had to have a way to poke a hole in the inner vacuum container without letting either our cabinet gas or the room gas get in. And so here's where we partnered with ESA this time, and they built us this piercing device, which looks a lot like the outer vacuum container on purpose, and it has this stainless steel chisel, which they hate it when I call it a chisel, but that's what it looks like to me. And so this attached to the end here, and then you use a torque wrench on the end, and you crank it down, and you poke a hole in it. I've just taken 2 years of work and reduced it to 2 sentences, but that's basically what happened. And so here's that piercing tool with the inner vacuum container inside. Here's where the torque wrench goes on the end. It's all hooked up. We pumped it back down to low vacuum. We pierced it. We heard a nice popping noise. It turns out the inner vacuum container leaked. No one was surprised, because that type of container is not designed to hold the vacuum for 50 years. But the outer vacuum container didn't. So we ended up sampling the inner vacuum container gas into these and the outer vacuum container gas into these. It's probably all the same gas because it had 50 years to equilibrate between the two. Didn't know that at the time, but now we have lots of gas from the moon. They're still studying it, but the short answer is there's no evidence of terrestrial contamination. There is some evidence of our cabinet gas in there because that's how the outer vacuum container was sealed, but they can still see the intrinsic lunar gas in there. And it's one of the first times that's ever happened. So that was so after we did this, how am I doing on time? Oh, I'm behind. Okay. We now it was time to open it up and get the dirt, get the part I care and Andrea cares more about out. But before we did that, we used our CT scanner at Johnson Space Center to scan the bottom because we had pierced a hole in the bottom. And what we needed to know was whether we had poked a hole through this. So this is a Teflon cap that the astronauts put on the moon. And if we had when you're going to see a pierce come in right here, and that's the hole we poked into the tube, and you can see it start to deflect. And what we were worried was we had shattered this Teflon cap. If we had, when we tried to pull the tube out, all the dirt would fall out the bottom and we would lose all of our stratigraphy and it would have been no good. So it didn't break, everything was good, we were all set. And then, just for fun, and because the engineers asked us to, now we don't listen to the engineers very often, and I do know what kind of school I'm at. We don't listen to the engineers very often, but we did this time. We scanned the top because they really wanted to know more about that metal knife edge seal and how well it worked, and they wanted to build a better mousetrap for Artemis. And so we were doing this scan, and we took it, and it came out pretty nice. You can see the stainless, whoops, that's not the right button. Oh, I'm not sure we have time to do this again. Well, right. Ignore the one on the left. We don't care about that one anymore. So here you can see the top of the thing. You can see the metal knife edge right here. Right here, where this is a stainless steel ridge, and there's an indium silver alloy in the top, and that all looks good, and we took the scan, and we gave this over to the engineers, and then the guy who runs the CT scanner looked at it, and he thought, and he noticed a problem. Because the next thing we were going to do is open this and take the aluminum tube out, and we were going to drive to Austin, and we were going to take a scan there, and now we go to the next slide, and what he noticed was it wasn't seated properly. Basically, the Apollo astronauts didn't do their job. Don't tell them I said that. But there's too much material in here. So this thing is what we call the keeper. It's just a thing that's designed with these stainless steel tines on it, and they're supposed to grab the edges here and hold the dirt in place. But they overfilled the tube, and these aren't grabbing onto anything, and it's just all floating there. So if we had taken the top off and pulled the tube out, it would have not been contained, and we would have shaken it up and lost our stratigraphy again. So that changed a lot of what we had to do about it. So this was a really good use of CT scanning and why it was really important. And then the next day, Andrea stayed in Houston to figure out how to open a tube like that, and we took the tube to Austin, so drove it across Texas. That was fun. Nothing like driving in a car across Texas with one of the last moon rocks and ever to be opened. It was supposed to have stayed inside. It was supposed to just be in the aluminum tube. We had worked with the CT lab there. They have a better CT scanner than we do, and they had made all this practice, and like 18 hours before we showed up, I called them and I was like, you know all that practice we did? Yeah, we're going to show up with it in the stainless steel tube. Can you still do it? And they did. And what you're going to watch now is a scan starting at the top, going down. There are 26,000 slices in here. Each one is one of the many, I haven't really explained what CT is. So X-ray computed tomography is actually relatively simple. If you've ever had a CT scan at the hospital or an X-ray scan, it's exactly the same process. We have source for X-rays on one side, we have the sample in the middle, and a detector. We scan the X-rays through the sample. Some of the X-rays are absorbed. We take two-dimensional snapshots. We repeat that process 3,000 times as we rotate the sample. And then we use magic, three-dimensional software, to reconstruct them into movies like this. Now I've talked through my entire movie. But what you were able to see as you went down through is we were able to check and see if there were any big void spaces, if there were any angular fragments. It also is going to serve as a permanent record of what was in the core tube, because we have to push the material out, and doing so will disturb it, and this was a nice permanent record of that. All right, I have to keep going. Right, so now I'm getting to the part that took most of the time, and then I'm only going to spend 2 minutes on talking. So this is the part we had done before. So physically dissecting the core. So we've taken the gas out. We know it's safe to open it. Now we have to open it and push the dirt out and then subdivide the dirt into many different intervals. And so we hadn't done this in 25 years. It turns out Andrea, who's sitting here in the front row, and you'll get a chance to meet when we're out in the hall when we're doing the sample thing. She also told me not to introduce her, so yeah, I don't listen. We hadn't done this in 25 years, so we built an entire mock-up. We spent about 8 months. We had to find all of the equipment, which we hadn't used in 25 years, clean it, replace it, practice with it. It took us about a year to get ready to do this, even though we had done it before. It took us 3 years to build the gas extraction manifold and all of that. So time is important. So we built all of that, and then we brought it up into the lab, and then you're going to see my main contribution to the entire process. You can see Andrea, she's here. They're in the process of opening the steel container. It's all very delicate work. This is me saying you missed a spot and just hovering in general and getting in the way. And so we spent most of a day, and you very carefully extract the aluminum tube, which you can see here being handled. You have to remove the top and the bottom. You put new special end effectors on it, and then you strap it into this thing. You turn this wheel, which pushes a plunger, which pushes the dirt into this receptacle. Again, I just took a day of work at a year of practice and reduced it to like one sentence. That's what we did. And in the end, everything worked great, even though we hadn't done it. And so I said we weren't going to talk about 73002. Here's that one, and here's 73001. So we did it twice for both cores. It worked really well. And so you can see the relieved groups of people all around who helped in the process. Some of us helped more than others. And so the next step was to start at one end, and then Andrea and the other processor would take a spatula, mark off a 1/2 centimeter interval, and they would very carefully scoop all of the material out in a 1/2 centimeter interval. We would then sieve that into different size fractions, and then we would repeat that process every 1/2 centimeter. The entire core was almost 100 intervals long. Each one was divided into 5 different size fractions, and then we repeated that process twice because we do it and we do it again. So we turned 2 samples into 1,000. And so, but it all worked really well. And this part wasn't really different from how we did it before, except for we were able to seal some of the samples in the bags and then take them down to our CT scanner. Now, everything, if you look carefully here, everything's covered in dust. And so not to brag, but I'm a fairly experienced lunar geologist. I can usually look at a lunar rock and tell you what it is just by looking. But I can't do that if it's covered in dust because I don't have magic eyes. And so that's where the CT scanner once again sort of came to our rescue, because each one of those bagged individual 4 millimeter particles was taken to our CT scanner, and it was run through the scan, and now you can understand. Now I know that that's a basalt on the left and a regolith breccia on the top right, and what we call an agglutinate on the bottom, and there's about a dozen different lithologies. This is super important because these are the main, like, people want to study the fine material in the core, they want to study the coarse material, but they really like this coarse material, and they have very specific goals. They need a basalt to do this, they need a northsite to do this, they need a breccia to do this. And rather than guess and just hand them particles based on, our best guess, we were able to scan them and definitively give them what they need and not waste any samples. We did this for 350 different particles. And so the guy who runs the CT scan, I'm going to skip these because I know we're behind on time. So ultimately we were able to get very detailed different types of lithologies. We were able to map where in the core they came from and learn something about how it changed with depth. And then the last thing we did very quickly is we did what's called multispectral analysis of this. And so we had, again, we don't do this is not our expertise, so we invited a group from the University of Hawaii to come in, and they had built this special rig and they put it on top. We had to turn all the lights out in the lab, which was fun. We never do that. And then he scanned along the length of the core using 6 different wavelengths, which match the wavelengths they used in orbital measurements, and then they were able to make maps like this. And so things that wouldn't be obvious to the naked eye are obvious in this. And without going into the details of what all the numbers mean, what it shows is that the top of the 73002 core has one layer at the top and a different layer at the bottom. That wasn't unexpected. The fact it's not horizontal, the fact that it's on an angle, was unexpected. It should have been flat, and this is probably from a disturbance. They were also able to spot most of the other core ended up looking pretty much exactly the same, which is still a result, not a great result, but there was one spot that turned out to be really important, which we might not have noticed had they not done this. And so this was just another way to add technology to do better scans. So we're a little behind, and so I'm going to do what I usually do when I give these talks and skip most of the frozen part. So everything I've just talked about for how we process samples, we do in our shirt sleeves, in a lab. It's easy. Well, it's not easy. I can't do it, but it's easy for people who are well trained at it. Now we wanted to do that exact same process inside of a freezer, and that presented a whole bunch of problems. It turns out if you take your cabinet and you freeze it, then everything leaks because, well, turns out metal shrinks. Who knew? Turns out every engineer in the world. But so we had to redesign the entire cabinet to work at minus 20 degrees Celsius and still hold a vacuum or hold pressure well, because now you're in a tiny metal box, a freezer, pumping it full of ultra-pure nitrogen, which has no oxygen in it. So you don't want to asphyxiate the people who are working in there. So we spent a couple of years figuring out how to retrofit our cabinet, and eventually we stuck it into a freezer, and then we had to decide whose job it was to go into the minus 20 freezer and process the samples. Now, Andrea's from Houston. My other processors are from like Louisiana and other parts of the South, and I'm from New York, and Jeremy, who you can, the lucky loser here, he's from Michigan, so we're up top. So we were voluntold that we were going to be the ones processing it. So the actual processing part was basically exactly like we do it in the normal lab. We're just doing it at minus 20 for 30 minutes at a time before we can't feel our fingers anymore. Then we go out, we warm up, and we repeat the process. So it all worked really well. So cold processing is good. We did all of this in a temporary facility, and we're in the process of building a new facility that will be the permanent home for that. So INCSA worked really well. We learned some important things. They got a lot of good science out of it. We learned that everything takes time. We already knew that. But so as we get ready for Artemis, things we have to relearn, that takes a certain amount of time. Things that we, he's creeping towards the stage, and I haven't gotten to part 3 yet. Anyway, so interlude 2 will be very quick because I'm talking about this. All right. There's a huge group of people who did that. So, all right, now the last thing I want to talk to you about is Artemis. Now if you think, wow, these look like professional slides, they are. So all the other slides, I made those and it looks like it. Now I have slides from NASA Public Affairs and they look really fancy, it's really great. So we haven't brought the Artemis samples back yet. So my plan was to talk about Artemis samples, but then I realized there aren't really that many. So what I will do is give a very high level briefing about the rocket and some of the other major components of Artemis. I'll talk about the timeline, and then I'm going to give up because I am not an expert in these things. But they're still fun to look at. So the whole point of Artemis is to go get more moon rocks. Oh wait, that's what I think it is. Turns out that is not official NASA messaging. That's Ryan's official NASA messaging. Artemis is going to go get more moon rocks. What Artemis is really going to do is teach us how to work in deep space. NASA has an ultimate goal to get to Mars, and then they realized going to Mars first wasn't going to work. So going to the moon and learning how to do all this on Artemis on the moon is going to be really important. And so you have to develop things like the rocket, the spacecraft, all the lander, all the other things. So not all of these are built yet, and I don't know enough about most of them to give a competent talk, but we'll talk about the 3 I felt comfortable enough to talk about. First one is rockets. So we don't have any more Saturn V's. Well, we do. They're sitting in our museums. So what they did is they built the SLS, the Space Launch System, which is modern. Like where you had, and you have space. And it going to land and collect samples. Artemis 4, we're going to basically do the same thing, but we're going to go to Gateway on the way, which is like the space station, but not in orbit. Also not official NASA messaging. And then Artemis is 5, they're going to have a rover. Artemis 7, they're going to have a freezer. Artemis 8 or 9, they're going to have a pressurized rover. So they have this whole thing planned out for what they're going to do at the South Pole. And here are the landing sites that they might go to. There's like 13 different spots, all at the South Pole. No one's decided where they're going to land yet, but that probably won't be decided till 6 months to 8 months out, hopefully by then. There's a lot of different reasons to bring samples back, and we think there's a lot of volatiles at the South Pole. There's a lot of really ancient impacts there, and the fact that we only landed on the near side and now we're going to land right near the far side will really increase our coverage. And so with that, this is the Artemis science team internal science team that I'm part of, and you don't need to see that. Here's part 3 summary. I went way long, I'm sorry, and thank you for your attention. I'm happy to answer any questions, and we'll be out with the samples this afternoon, so if you don't want to ask the question in front of the whole room, ask us later, we'll be around. Thank you.
Thank you, Dr. Zeigler. It's truly been fascinating. And as you mentioned before, it was really cool. It was truly cool. And before we continue with the order of the day, I'm seeing hands raised. We're going to answer just a few questions before we continue with the order of the day.
First of all, I would like to thank you for coming here and, well, giving this talk. I personally and every attendee here, we do believe that your work is really important for humanity. However, my question is, how would you explain the importance of your work or missions like Artemis to people who are not really much into science, to the average person?
That's a really good question, and it's one that's a little bit hard for me to answer as a geologist. Apollo caused many amazing technological achievements. Velcro, but that's silly, but how many times do we use it? It revolutionized computers. It taught us how life support systems work. So there were a lot of technological advances that came out of the Apollo program and have continued to come out of the space program. So the studies of the rocks themselves are less tied to that. But I only talk about the rocks because that's the part I love. But there were many technological achievements that went along with that I'm not quite as familiar with. So that's not a very good answer, but they do exist, and I can try to find out more for you. And thank you. I'm really happy to be here. I'm excited.
Okay. Thank you very much, Dr. Zeigler. Very fantastic presentation. My question is very simple. What is the most challenging aspect of curating lunar samples?
That you only get to have one bad day, I think is it. So each of the individual parts are relatively straightforward. Like, we know how liquid nitrogen works, we know how air handlers work, we know how ultra-pure water works. But if we had a malfunction and we flooded the samples with a bad gas, or if we weren't paying enough attention and someone brought material into the lab that had a lot of gold in it or some other element, that those samples would be ruined. At least they would be ruined for those particular measurements. And so the fact that that's a lot of pressure to not goof up. And so from a technological standpoint, it's relatively straightforward, but you don't get to have more than one bad day. So I think that's my answer. Andrea may have a different answer.
Hi, Ryan. Thank you very much for coming again. Could you please tell us a little bit more about the gases in the samples?
Yes. So we had hoped that, I didn't really talk about it, but I showed the map, and where the sample was taken was above a fault. And on Earth, gas escapes out of faults from deep within the Earth. And so we were hoping that on the moon, there was gas escaping from inside the moon. The other source of gas in lunar regolith is from the solar wind that's being implanted there. They haven't finished the analyses yet, but right now, all we're seeing is the signature of solar wind gas. And so what's interesting about that is that this sample came from relatively deep, about 35 centimeters below the surface, and people were a little surprised to see this much solar wind this deep within the regolith. So right now, the lunar gas measurements are telling us more about the sun and how the sun interacts with the surface of the moon than about the moon itself. I think to answer the gas from the interior of the moon question, we're going to have to use the Artemis samples to do that, where we don't have our cabinet gas mixed in. Like, we don't have to wait 50 years when we get the Artemis gas samples back to study, and so studying them immediately will give us better sensitivity, and we'll have a better chance of studying the gases that are leaking out of the moon itself. And so,
thanks. Also, I would like to congratulate you for the excellent presentation. And my question is regarding about the special metals that may have been found during your years of working, because it has been said about solar wind and water, but what about special metals that could help different projects on Earth regarding developing certain technologies?
that's a great question. So it turns out that most of the processes on Earth that make ore deposits that highly concentrate different metals or different elements don't work on the moon, because they usually involve liquid water. So if you're going to have a copper or a gold deposit or platinum group elements, there's usually a water cycle involved, and we don't have that on the moon. So we don't seem to have highly concentrated ore deposits on the moon. We find trace amounts of some of these very special metals like platinum nuggets and stuff, but those are coming from the meteorites that are hitting the moon and are more of a record of the meteorites than of the moon itself. People talk a lot about mining on the moon, and that will be very good for major elements, iron and titanium, things you might want to build your base out of. But it costs so much to get material to and from the moon that right now it seems like the only viable use for those is on the moon itself to build the base. So titanium mining on the moon to bring it back to Earth, there's 100 years of titanium mines in Canada and other places that we have to deplete those first. And so I hope that answered your question.
Hi, Doctor, here. Thanks so much for your presentation. It was pretty fun to hear all of that and full of content. My question is specifically with the most interesting regions of the moon to collect samples from.
Oh, the most interesting regions. I mean, the South Pole is certainly high on the list because it has maybe enriched volatiles and because it is near the far side of the moon. Another area that I really want us to go back to is Aristarchus, which is on the near side of the moon. It's in the northeast quadrant of the moon, and it is an ancient plateau that sort of sits in the middle of the mare. And there's a lot of really interesting rocks and unique types of rocks that we've seen from remote sensing. Right now, Artemis is only planning to go to the south pole of the moon, but everyone at NASA would love to go to other parts of the moon as well, but everything is being designed for the South Pole. So what they're going to do is land at the South Pole first, and then they're going to figure out how much flexibility they have to land other places. And so we have been making the case why going to Aristarchus should be at the top of the list. So.
Okay, just one more question. Just with my... Well, hello, and thank you for your presentation. I would like to know, how will the recollection technology in samples will change from the previous mission to the Artemis mission?
How will the collection technology?
Yeah.
Not much. So they designed the tools for the Artemis missions by taking the Apollo 17 tools and updating them. And there was talk about updating them to, say, new metals, where we use stainless steel and aluminum on Apollo. You could use something like carbon fiber, or which isn't a metal, but carbon fiber or titanium alloys. The problem with those is those have an unknown contamination profile. We know what aluminum and stainless steel does to samples, and we know that it doesn't right now interfere with any of the measurements we want to make. So in the end, they made slightly updated versions of pretty much all of the Apollo tools for the Artemis tools. Now, the company that's building these is Axiom, the same people who are building the spacesuits, and they're not done yet. And so we've been working with them, and they've been really good partners, and they're really excited to get some good samples. So I'm actually kind of glad they did that, because a hammer is a hammer, and you have a tendency to overthink it, and we avoided that, and so I think that was good.
Okay, thank you very much. Unfortunately, our time is over, but we've had the time of our lives. And I just want to say thank you. Thank you for being here, for giving your time to us, to this public, to this space, to UPAP. We are truly grateful. And as a gesture of gratitude, we're going to give you a little present. It's representative of Puebla. It's dulces típicos in a plate of Talavera and a t-shirt.
Thank you very much. Thank you very much.